Good evening, everyone. I'm Calvin Joseph, and today I'll conduct your Week 5 problem solving and doubt clearing session for this course, Digital Electronic Circuits. Okay, so we will look into what was taught by Sir. We will also solve some sums, example sums, assignment sums, and that's the target for this session. So, in the Week 5, you had considered various aspects. One was number systems. So basically, we are very used to the numbers that is 0, 1, 2, 3, all the way to 9. Okay, this is our normal decimal system. But when we come to computers, they are binary, right? They are just binary. So binary means what? You have 0 or 1. So to do that, so to represent 0, so you use 0, 0 stands for 0. 0, 1 stands for 1. 1, 0 stands for 2. 1, 1 stands for 3. Okay, so this is like for a simple binary representation. But now, if you want to represent, let us say 36. Okay, if you want to represent 36, what you will have? You'll have, and you have 8-bit numbers. Okay, 8-bit numbers. So you have dash, 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 dash. And you have to find its binary equivalent. So this is 2 raised to 0, this is 2 raised to 1, this is 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7. Now, 36 can be written as 32 plus 4. So since 36 is 32 plus 4, it is what? 2 raised to 4, 8, 16, 32. It's 2 raised to 5 plus 2 raised to 2. That means 36 is actually 0 into 2 raised to 0 plus 0 into 2 raised to 1 plus 1 into 2 raised to 2 plus 0 into 2 raised to 3 plus dot 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 plus 1 into 2 raised to 5 plus dot 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 plus 0 into 2 raised to 7. That means it is 0, 0, 1, 0, 0, 1, 0, 0. That is what 36 means when you represent it in terms of binary. This is the representation of it. Now, if you want to represent it in terms of an octal representation, so there are also representations such as octal representation, and there is a hexadecimal representation. Okay. So now, for the octal representation, let us consider octal means 8. Okay, so that means the numbers are going from 0 to 7. So this would actually use 3 bits. Okay, 3 bits. So you have 0, 0, 0 stands for 0. 0, 0, 1 stands for 1. And so on. You have 1, 1, 1 stands for 7. 1, 1, 0 stands for 6. So now if you want to convert 36, its binary equivalent was what you saw, 0, 0, 1, 0, 0. Oh, 1, 0, 0. So this is in terms of 10, in terms of decimal. Okay. But this is in terms of binary. Same number, when you represent it in binary, it is in this format. Now you have to represent it in terms of octal. Octal. Okay. So how do you do it in this case? One simple way which you could use is you can write it down as you can group it in terms of bits, 3 bits. So you write it as 00, 100, 100. Okay. Now you take this is 3 bits, this is 3 bits. You add an additional bit 0, and this is another set of 3 bits. Okay. In terms of octal, 1000 represents 4. Right? This also represents 4. And this represents 0. So this is actually 0 into 8 raised to 2 plus 1, sorry, plus 4 into 8 raised to 1 plus, sorry, 4 into 8 raised to 0. So this number is what? 4 into 8 is how much? It is 32. And 4 into 8 raised to 0, 8 raised to 0 is 1, so 32 plus 4, so it is 36. So this is a very simple way for you to convert any number from binary to octal. So the conclusion is binary representation is easily converted into octal representation by grouping 3 bits. Okay, by grouping 3 bits. So this is the power of octal. So octal form, what you will write 36 in octal representation is 0448. So this is the octal representation of 36. Okay. Now, the advantage is you can write it 3 bits, you can combine. But many times you have 4, 8, 16 in this format. So then there was another representation which is known as the hexadecimal representation. Hexadecimal representation. What does hexadecimal representation deal with? It considers 4 bits. Okay, it has 4 bits. So what it does is 0000. This again is 0. 0001. This is 1. 0010. This is 2. Okay, very good. It goes on like that. Then you come to 1001. This is 9. Till here it is very simple. It is as we know it. But then now you go to 1010, 10. How do you represent 10? So for that, they write it by A. A represents 10. Similarly, when you further do, you do 1011. That is, so this is actually 10. This is B. This is 11. Then you have 1100. That is your C, which is your 12. Then you have 1101. That is your D, which is your 13. Then you have 1110. That is your E, which is your 14. And then you have 1111. That is your F, which is actually your 15. Okay. So this is the table for your hexadecimal representation. So what is the power of hexadecimal representation? What is the advantage which we get when we do hexadecimal representation? Let us take a very simple example. We'll take the example which we consider, that is 36. 36 in 10, it is in binary equivalent. What do we write it as? 0010, 0, what is it? 100. So this, we take this 4 bits and this 4 bits. So this actually represents 4 and this represents 2. So when you want to, so what is, does this mean? This is 2 into 16 raised to 1 plus 4 into 16 raised to 0. So that is 32 plus 4, that is again 36. So 36, when you represent it in terms of hexadecimal format, you get it as 2, 4, and 16. So this is the hexadecimal representation of 36. Now, why don't we think something else? Let me say, what does this number mean? This number, let us say BA3 hexadecimal version. What is this magnitude of this? So this means first let us start with 3. 3 into 16 raised to 0 plus A. A means 10. So 10 into 16 raised to 1. Then B means 11. So 11 into 16 raised to 2. So what is 16 raised to 2? So it is 11 into 256 plus 10 into 16 raised to 1 is 160 plus 3 into 16 raised to 0 is 3. So when you add it, what will you get? 11 into 256, let us say this is 2560 plus 256, okay, plus 163. When you add it, you will get 9, 12, 17, 7, 1, 6, 8, 9, 9. So it is 2979. So this means the number 2979, you could represent it as 10. You could represent it is using BA316. Okay. Now, you are told you have to convert this to binary. It is very difficult to convert this to binary, but you already have the hexadecimal representation. So what we do is this BA316, which actually stands for 297910, you will represent it as 4 bits. So 0000 means bits. This is for B. Then you have this for A, and then you have for 3. This is for 3. So 3, how do you write? You write it as 1100. A stands for 10, so it is 1010. And B stands for 11, so it is 1011. Okay? So you should just think, if I give you this number, I give you what number I give you? I give you 1011, 1010, 0011. This is the binary representation. I tell you, you find what is the value. What does this signify? It is very difficult. But if you write it in a compact form like this BA316, this is easier for you to, it is easier for you to visualize, it is easier for you to understand, etc. That is why they came up with this format, that is the hexadecimal representation. Okay. So then you can have what is known as fixed point and floating point. Fixed point and floating point. Fixed point means, let us say you have 8, 4. That means you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 bits, okay? But your point, that is the 4th one, that is over here from the right side, 4th one, okay? So let us just take a number. Let us say we have the number 10110101. Okay. So what does this number mean actually? What is the significance of this number? This means this is 2 raised to 0. This is 2 raised to 1, 2 raised to 2, 2 raised to 3. This actually is 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4. So this number, which is we write it as, it is actually 8, okay, plus 0, plus 2, plus 1, plus 0. 2 raised to minus 2 is what? 0.25. 2 raised to minus 3 also is 0. 2 raised to minus 4. That would be, what is that? 0.0625. Okay. So the number which you get is actually 11.3125. Okay, so to represent 11.3125, we use this kind of data type. That is, it is a fixed data type. Okay. So what is the range? What is the range of F8, 4? Range is when, what is the maximum value? What is the minimum value? Minimum value, since we are considering unsigned in this case, minimum value is 0 when all the bits are 0. Maximum value is when all the bits are 1. So that would be like when 1111.1111. So you can add it. It would come very close to, it'll be approximately 32, but not exactly 32. It would be, let us say, some 31 point, let us add it. So 31 is the part over here, and the fractional part will actually be 0.5 plus 0.25 plus 0.125 plus 0.0625. When you add the fractional part, it becomes 5, 7, 7 plus 6, 13, 6, 7, 8, 9, 0.9375. So the range is actually from 0 to 31.9375 when you use this representation. Okay. Now, and what is the resolution? Resolution is the accuracy, like what small value you can detect, which is the smallest value you can represent using this. So that is actually 2 raised to minus 4. Okay, that's the smallest change. That is the least significant bit what it represents. That is your resolution. So 2 raised to minus 4 comes out to be 0.0625. Okay, so this is the representation. Now, in floating point, there is something known as a mantissa and an exponent. So the exponent, what it does is, it has, so there will be some number of bits for the mantissa, some number of bits for the exponent. Okay, so exponent is like the power of. That can say it is 2 raised to power of 5, 2 raised to power of 6, etc. Mantissa is the smallest accuracy. So mantissa deals with the accuracy. Okay. So what happens is when the range is small, floating point accuracy also is like as you need. It is also very small. But when the range is large, the accuracy is, or not the accuracy, the resolution. The resolution also is large. Okay, so there are certain drawbacks of floating point, there are certain drawbacks of fixed point. Fixed point means you have a very limited range. Floating point means you can have a larger range, but then you are constrained. You are constrained with, you're not constrained, that there are certain resolution issues when you're multiplying large numbers, the resolution is larger and smaller in that way. Okay, it floats. That is, your decimal point is sort of floating. Okay, in fixed point, the decimal point is fixed. In floating point, the decimal point is floating. Okay. There are some people who say you should only use fixed point. Some people use floating point. Floating point, when you use, you need that floating point hardware, which will implement floating point. Fixed point is relatively easier for the hardware to implement in all. So there are certain cases floating point hardware is there, certain cases it is not there. It depends on your application. Okay, but this is just a small representation of what is possible in digital multiplication, etc. Now we consider till now only unsigned numbers. Okay, we consider only unsigned numbers. That is, we'll just take a small example. You may know it also very well, but let us just consider. You have, let us say, for 3 bits. Okay, you have 000, 001, 010, 011, 100, 101, 110, 111. So what does this mean? This means it is 0, 1, 2, 3, 4, 5, 6, 7. So that means your range is from 0 to 7. But life is not, always positive. There are certain times things are negative and etc. So numbers and in the various hardware, various algorithms, various everything which you do, there'll be negative numbers. So you need to represent the negative numbers. So what is done is there's a concept known as one's complement. One's complement. Okay. Okay. First, let me tell you. So 0 to 7 is the range for unsigned. But when I go for signed numbers, I need an indicator. I need something to tell me that is the number signed or is a number positive or negative. Here it is always positive, right? So I can take it for granted that my number is positive. But when I go for signed numbers, I need something to tell me whether it is positive or negative. So I need an indicator, an indicator. And in digital, what do we have? We only have bits, right? And now my decision is either positive or negative. So I need two options. So I need one bit. So I need one bit, which is also known as your sign bit. Okay, I need one bit, which is known as your sign bit. So what is done is your MSB. MSB stands for your most significant bit, right? So this most significant bit represents whether it is positive or negative. So if your MSB is 0, it means your number is positive. If your MSB is 1, it means your number is negative. Okay? 0 means it is positive, 1 means it is negative. Okay? All right. So now let us consider this case. Okay? Which is the color. So this means it is positive and the number is 0. There's no problem. It is 0, 1, 2, 3. But now I have 1000, like 100. What does this mean? Right? So in one's complement form, like there is a representation known as one's complement. Or just a sign representation. Let us say sign. It says you say this 2 bits 0 0 means 0 and 1 means the 1 bit is the sign, so this again becomes 0. Like it's kind of like minus 0, which is still 0. This is 0 1. 0 1 means 1 and here it is 1. Sign bit is 1, so it is minus 1. So similarly this is minus 0 minus 1 minus 2 minus 3. Okay, 0. This is the case. Now there is another way, which is you can have one's complement. One's complement is what? If you have, let us say 0 1 0, this is 2, right? I want to find minus 2. What I do is I invert the bits. So this becomes 1 0 1. So this signifies, so what has happened is this sign bit has changed. That's changed it, so I know it is negative. And whatever was 2, you just invert all of it, you get minus 2. That is the representation of one's complement. You will also be knowing this. Next, you have something known as 2's complement. Okay, 2's complement is very widely used, very popular. 2's complement, let us say, let us take the number 3. Or let us keep 2 only. Okay, this is the number. I want to I want to show negative minus 2 now. I want to show minus 2. So first what I should do, I should find the ones complement. So it becomes 101. This is the ones complement of it. Okay. Now I want to convert it to two's complement. So I just add 1. So this becomes 0. This becomes 1. This becomes 1. So this means minus 2. This signifies minus 2. Okay. Let's take one more example. I have 0, 1, 1. This is for plus 3, but I want to represent minus 3. So I make this 1, 0, 0. Okay, this is the ones complement of it. Then I'll add plus 1. So this becomes 1, 0, 1. So this signifies minus 3. Okay, this signifies minus 3. So these are the various, so we saw various representations. So now let us see the range. Let us see the range. Okay, one more point I have to add. Two's complement is easy for us to understand what is the value of it. So how do you do that? Two's complement means this is 2 raised to 0. Okay, let me draw better. Say this is 101. This we know in 2's complement, it means minus 3. But 2's complement has an advantage. You can actually easily get a number value. So this is actually 2 raised to 0. This is 2 raised to 1. This is minus 2 raised to 2. That means this number is 1 into minus 2 raised to 2 plus 0 into 2 raised to 1 plus 1 into 2 raised to 0. What is that equal to? Equal to minus of 4 plus 1. So that is equal to minus 3. So this is the 2's complement representation. So if you have the 1's complement representation, you have to invert it and check it. 2's complement is this is the way. You can easily find out what is the magnitude. Okay, this is a simpler, easier, like this is a very popular one, which if you use extensively and if you practice a lot, you can easily understand how it is done. Okay. All right. So now, what is the range? If you have bits, that is, you have you have 3 bits. This. It is maximum value is max is positive is when sign bit is 0 and all bits are 1 1. This signifies plus 3. And what is your minimum value which you can represent? That is sign bit is 1 and all the other values are 0. So this represents minus 4. So your range in this case is from minus 4 to plus 3. Okay. This is your range. All right. So, sir has also taught how you can do addition and subtraction. The various, hardware circuits which will do your addition, subtraction, all these things are there. Okay. So what we'll do is we'll start with the sums and we'll focus on these numerical sums, based on a number system representation. Various sums are there. We'll try to understand it and then we'll proceed. So question 1. So what is the hexadecimal representation of 32178 and 76458? Okay. So how do we represent it? So easy way, okay, to get started with this is you have 3217 8, right? So what is this actually? 3 into 8 to the power 3 plus 2 into 8 to the power 2 plus 1 into 8 to the power 0 plus 8 to the power 1 plus 7 into 8 to the power 0. So this is actually 3 into what? 512 plus 2 into 64 plus 8 plus 7. So 512 is 6, 3, 1536 plus 6, 128 plus 15. So when you sum it up, it becomes 6 plus 8, 14 plus 5, 19, 9, 1, 4, 6, 7, 7, 6, 1, 6, 6, 7, 9. That means 32178. I can represent it as 1679 in 10. Okay. Now, similarly, you have 76458. That how do you represent? That is 3, that is 7 into 8 to the power 3 plus 6 into 8 to the power 2 plus 4 into 8 to the power 1 plus 5 into 8 to the power 0. So that also when you will add it, you would get a number of 4005. Okay, 4005. So that means 76458 is actually means 4005 in 10 in this 10 based format. Okay. Now, in the question, if you will notice, question is saying we want a hexadecimal representation. And this is MCQ based. You don't have steps. You are given options. So this is first option, this second option. Like two values you need to find. It's like a fill in the blank. So here it is either 69F or 68F. Here it is FA5 or FB5. Okay, so instead of going through the long process of converting 1679 into hexadecimal and of 4005 into hexadecimal, let us go through the other way. Let us try. Let us say we have 69F. Okay, we want to find its magnitude in 10 in terms of this 10 number system. So this is 6 into 16 to the power 2 plus 9 into 16 to the power 1 plus f is 15. So 15 into 16 to the power 0. So this is what 6 into 16 square is 256 plus 9 into 16 comes out to be 144 plus 15. So this magnitude of this comes out to be 1695. Okay. It comes out to be 1695. Now, I want you to note that this is 1679, this is 1695. They don't match. They don't match. So you see the other option which was given was 69E, right? So it's 68F. Wait a minute. It's 69F and 68F. Okay. The option which was given is 68F, 69F. So this is for 69F. A bit off. This is for 69F, right? 1695. Once you have got this, now you have to find 68F. Okay, what is that? That actually is what? 69F minus what? 01016, right? So it actually means 1695 minus 16. So that when you will do 1695 minus 16, so 15 minus 6, it is 9. So 7. So it comes out to be 1679. So this is the number. So the first case, it is 68F. This is the number you need. This is the correct option. Now you have to go for the next case. Next case you have B, which is 4005. 4005 in 10th way. You have to convert it into hexadecimal 1. The options which you have given are FA5 and FB5. So the options you are given are FA5 or FB516. So let us start with FA5. FA516. You can write it as 15 into 16 square plus 10 into 16 raised to 1 plus 5 into 16 raised to 0. That is what? 15 into 256 plus 160 plus 5. Okay. So 256 is what? 2560 plus 5 into 256 is half of this. That is 1280 plus 165. That entire value is 5, 12 plus 80, 1, 6, 8, 9, 6, 7, 8, 9, right? And then you have 3. So this is 3905. Have you got this value? Check. So 20, 0. Okay, this is 2. Sorry, this is 2. So that's why this will be 4005. So this is the answer. So you need it. So the options are FA16, FA516, and what was the correct one over here? 68F16. 68F16. Okay, so these are the correct options. So when you go to the question, it is 68F16 and FA516. That is option B. Okay, that's option B. Now, let us go for the next part. We have to find subtraction. Okay, it's a subtraction sum. So this is the question. Okay, let us start with the first part. You have 7645 minus 3217. Okay, and this you must understand it is in 8. It's in terms of 8. This is a number 8 octal representation. So now when you let us do it in terms of 10. Let me signify what does it mean. If you suppose you are doing 7645 minus 3217 normally, what do? 5 is less than 7, so you borrow. So you make this 3 and you make this 15. You make it actually 15. 15 means what? It is 10 plus 5. 15, right? Now you subtract 7 from that. So you get 8. 15 minus 7, you get 8. So this becomes 8. Then 3 minus 1 is 2. 6 minus 2 is 4. And 7 minus 3 is 4. So this is a very simple thing. You get 4428. But this is when you're considering the number systems is in terms of 10. But when it is in terms of 8, you see 5 is less than 7. So you have to borrow. So this you take it to 3. And this actually becomes 5 plus 8. This 5 plus 8. So 5 plus 8 is 13 minus 7 is 6. So this becomes 6. 3 minus 1 becomes 2. 6 minus 2 becomes 4. 7 minus 3 becomes 4. So actually it is 44268. Okay. So it is either this or this. Now, similarly, what do you have to do? You have to do E5D9 minus C25B. Now, B is more than 9 because B is 11 and 9 is there. So D, you decrement it. So it becomes C. And then you give it 16 plus 9. So 16 plus 9 is 25. 25 minus 11 is 14. 14 is your E. 14 is your E. C minus 5 means you make it B, A, 9, 8, 7. So it is your 7. 5 minus 2 is 3. E minus C is 2. So 2, 3, 7, E. So it becomes 2, 3, 7, E, 16. So this is the one. So this is your answer. Okay. All right. So this is how you do subtraction. It is like the same concept which you studied when you were in school. Now I understand like why teachers find teaching maths so difficult to students. How you tell you borrow something, you bring something, put this point there, put that point there. It takes time. Okay, but since you guys are engineering students, you guys will be able to do it very quickly. Now we'll go to the next question. Which of the following statements are not true? Okay. Um, So which of the following statements are not true? Let us say it is either true or false. You have to write it. So what I was thinking earlier is I'll just write it whether it is. So what I said used to say, you write it as true or false. Okay, but that is a little bit confusing. That is a way you can do, but I thought the better way is write true and write not true. So I know what I'm exactly looking for. It is either true or not true. So let us say the first statement in fixed point representation with position of binary point are not defined. Is this true or false? This is this true or not true? This is not true, right? Next is floating point representation as fixed precision. This is also not true. So this comes here. The floating point representation comprises two parts, mantissa and exponent. This is true, comes over here. Fixed point arithmetic is similar to integer arithmetic. It is true, right? In floating point representation, gap between numbers is higher for larger numbers. That is true over here. So they are asking which of the following statements are not true. So not true is statements 1 and 2. Okay. So these are the statements which are not true. Okay. So now we'll go to the next question. The range of values in decimal that can be represented by fixed 16-8 point representation is. So so what is the range? You have to find the range. So 16-8 means what? You have 1, 2, 3, 4, 5. It's not visible actually. So blue color. So let us make it this. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So since if you see the 0 and this, it is like an unsigned number. Unsigned number means there's no sign, there's no concept of a sign bit. So we don't need to worry about sign bit. So the maximum value that this can take is when all are 1 and when all are 0. All are 0 is same. It is very easy. All are 0 is the minimum value. Now we want to find what is the maximum value means all are 1. Okay. All are 1. Hmm? So now this is 2 to the power 7. Okay. This is 2 to the power 0. This is 2 to the power 1. 2 to the power minus 1. This is 2 to the power minus 8. All right. So the maximum value in the integer side you can get it easily as 2 to power 8 minus 1. That is 256 minus 1. That is the 255. Now, we have to be concerned about the fractional part, right? About the fractional part, what is the maximum value which it could go? So then, if all are 1, should be a better way to do this. Because it could be 2 to the power minus 1 plus 2 to the power minus 2 dot 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 till plus 2 to the power minus 8. So this is actually a geometric progression. So it is geometric progression. What is the formula? It is a upon 1 minus r. If I'm not wrong. So a upon 1 minus r. Um, this is 1 plus 2 to the power minus 1 dot plus 2 to the power minus 7. How do we find this? Hmm, 1 upon 1. Do you remember what is the formula for geometric progression, sum of geometric progression? The very simple formula I've forgotten, lost touch. Just check. Geometric progression sum formula. So that is a into r raised to n minus 1 upon r minus 1. And if r less than 1, okay, I was using a upon 1 minus r, but it is a into r raised to n minus 1 upon r minus 1. Okay. So it is so your r actually is 2 raised to minus 1 and your n is 7. So a into r raised to n minus 1 upon r minus 1. R raised to n minus 1 into r minus 1. This 2 raised to minus 1 into 2 raised to minus 7 minus 1 upon 2 raised to minus 1 minus 1. So that is some 2 raised to minus 1, 2 raised to minus 7 minus 1 upon 2 raised to minus 1 minus 1. This is 0.5 into 1 minus 2 raised to minus 7 into 1 minus 2 raised to minus 1. This is 0.5 into 1 minus 2 raised to minus 7 upon 0.5. Cancel it. Sum is 1 minus 2 raised to minus 7. So 2 raised to minus 7, you have to compute it, and then you can get what is the sum. So your number is actually equal to 255 point, and this point part is actually 1 minus 2 to the power minus 7. So calculator is required. Let me just check. Calculator. If you do it, 2 raised to minus 7 is 7.8125 to 10 to the power minus 3. And into minus 1 plus 1, that is 0.9921875. So it will be 255.9921875. Okay, so this is the answer. Let us check the options. Oh, we are not getting that option. So, Let me just revisit it. So we wanted to find 2 raised to minus 1 plus 2 raised to minus 2 plus dot 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 plus 2 raised to minus 8, right? So let's say n is 8 actually, and a is your 2 to the power minus 1. So it is actually sum is a into r raised to n minus 1 upon r minus 1. So it is 2 raised to minus 1 into 2 raised to minus 8 minus 1 upon 2 raised to minus 1 minus 1. Okay, so it's just not 2 raised to minus 7, it is 2 raised to minus 8 minus 1. So this actually, when you will do it, will become 1 minus 2 raised to minus 8. So that is means your sum is 1 minus 2 raised to minus 8 is actually 0.99609. So that means your answer of the range is 255.99609. Okay, so this is the answer. Okay, so this meeting will end in 1 minute. And then I will again restart this meeting. So you have to join in the same link. Since this is not a premium version of Zoom, there's a time limit. So once this meeting ends, I will restart the meeting with the same link and we will continue solving the sums. Okay. So we'll proceed to the next question. We have to find what are the values of P and Q. So let's see this. So we have this equation and we have to find the values of P and Q. So this is an octal, this is an hexadecimal. Okay. So this is the equation 2p3648 equal to 2afq16. So we have to find what are the values of P and Q. So this is an octal representation and this is a hexadecimal representation. So we will do by expanding it is a simpler way. We can expand it as well. So we start by saying, first of all, you see in terms of odd and even. Odd and even. Okay. If you see Q determines whether it is odd or even, right? Q determines whether it is odd or even. But now you see 4 means it is even. 4 means it is even, right? Because any representation, if you say octal, binary, anything, if it is into 2 to the power 0, into 8 to the power 0, into 16 to the power 0. So the one at the last, that is what determines whether it is odd or even, right? Now 4 is even. Now after the values of Q, what is given? 7, 5, 4, and 3. See, so 7, 5, and 3 are odd, so 4 is correct. Right? You can easily say that this is the correct option. You can do it. But let us try to be a little bit honest and let us try to do it. So we have determined Q equal to 4. So the sum is solved. Let's just see. Let's see how it goes on. So this is actually 2 into 8 to the power 4 plus P into 8 to the power 3 plus 3 into 8 to the power 2 plus 6 into 8 to the power 1 plus 4 into 8 to the power 0. This is equal to 2 into 16 raised to 2. A is 10. No, 16 raised to 3. A is 10. So 10 into 16 raised to 2 plus F is 15. So 15 into 16 plus Q is 4. So 4. Right? So what do we get over here? So 2 into 8 to the power 4 is a big number to compute. Is there a way to make it simpler? Is there a way to make it simpler? Just say, I think you'll have to use the calculator only for this. So one thing we can notice, 4 and 4 gets cancelled. They get cancelled over here. And we can, how do we do it? Okay, so 2 into a to the power 4. This first just the issue. Okay, let us say, let's try 2 into a to the power 4, right? Plus p into a to the power q plus 3 into 8 square plus 6 into 8. This is 2 into 16 raised to 3 plus 16 square, let's convert to 8 square. So plus 8, let us say, is equal to 2 into 8 into 8 cube, right? 2 into 8 into 8 cube plus 10 into 4 into 8 square plus 15 into 2 into 8. Okay, I'm just trying to make it easier. So this, that means just 2 into 8 to the power 4 plus p into 8 cube plus 3 into 8 square plus 6 into 8. That is equal to 2 into 8 cube plus 40 into 8 square plus 30 into 8. So what do we see? We see that this gets cancelled, right? Yeah, this is 8 raised to 4. So this is 8 raised to 4. So this gets cancelled. So now we still have p into 8 to the power 3. That is equal to 8 square into 40 minus 3 plus 8 into 30 minus 6. 30 minus 6. Yeah. So p into 8 into 8 square is 8 square into 40 minus 3 is 37 plus 8 into 30 minus 6 is 24, right? So this p into 8 into 8 square is 8 square into 37 plus 8 into 8 into 3. So this is again p into 8 into 8 square is 8 square into 37 plus 3, right? So 8 square gets cancelled. So p is equal to 40 upon 8. That is equal to 5. Okay. So this is the way. So I'm going through this pain and through this length to do it, manually. Because in the gate exam, not the gate exam, sorry, the digital electronic circuits exam, it is that online calculator. It is a little bit tedious to do, compute. So as much as possible, I prefer to do manually. It takes time, but it's something, and it also can lead to errors, but you can be careful. Okay. So this is the question. Let us go to the next question. Okay. Screenshot. So this is the question. So 2's complement representation of P. So P is 1 1 1 1 0 1 0 0. Okay. Now there is certain significance of this. You see, this is 2 to power 0, 2 to power 1. Use a different color to simplify. This actually is 2 to power 0, 2 to power 1, 2 to power 2, dot, 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 2 to power 6, and this is 2 to power 7 and minus 2 to power 7. Okay. This is what 2 to power 4, and this is 2 to power 5. So this value of P, when you go for in terms of normal representation, this minus 2 to power 7 into 1 plus 2 to power 6 into 1 plus 2 to the power 5 into 1 plus 2 to the power 4 into 1 plus 0 plus 2 to the power 2. Okay, this is the value of P. Now, what do we do with this? Is like, very bulky, scary. And what you can easily do is you can write it as minus 2 into 2 to the power 6 plus 2 to the power 6 into 1 plus 2 to the power 5 plus 2 to the power 4 plus 4, right? So this is actually minus 2 plus 1 into 2 to the power 6 plus 2 to the power 5 plus 2 to the power 4 plus 4, right? So this actually becomes equal to minus 2 to the power 6. Then you have 2 to the power 5 plus 2 to the power 4 plus 4. So what you could easily do is, if you will further proceed, minus 2 to the power 6 plus 2 to the power 5 is actually minus 2 to the power 5 plus 2 to the power 4 plus 4, right? And let me just do a simple one. So the minus 2 into 2 to the power 4 plus 2 to the power 4 plus 4. So that is 2 to the power 4 into minus 2 plus 1 plus 4. So that is equal to minus 2 to the power 4 plus 4. So what is minus 2 raised to 4? 2, 4, 8, 16, 32. So it is minus 32 plus 4. So it becomes equal to, what is the number of it? 2, 4, 8, 16. Sorry, minus 16. Okay. It is minus 16 plus 4, that is equal to minus 12. So your P in 10 is minus 12. Now divide by 3. That is what? Equal to minus 4. So you have to represent minus 4 in 2's complement. We have to represent minus 4 in 2's complement. So how do you do it? So let us just write, and the bits are given. It is 8 bits. So it is 0, 0, 0, 0, 0, 1, 0, 0. This is plus 4. Now what we do, we find the 1's complement. What is that? 1, 1, 1, 1, 1, 0, 1, 1. Then we have to add 1. That becomes what? 0, 0, 1, 1, 1, 1, 1, 1. So this actually is your minus 4 in 2's complement. Okay. So I hope this is clear. This is a very simple representation. They have a term known as signed bit extension and various other things they use in 2's complement and all. As you use it more in your work, in your project, in your studies, you'll get more comfortable with it. Okay. Now we have this question. This is the question. So you have A is in signed magnitude and B is in one's complement form. And what is the number? That is 1, 1, 0, 0. And this is 1, again 1, 1, 0, 0. Okay. Now what does this mean? What does this mean? So let us go one by one. So let us first consider signed magnitude. So this is what? 1, 1, 0, 0. This means you consider this the magnitude and this is the sign bit. So this means it is negative, and 1, 0, 0 in terms of magnitude is 4. That's why this is minus 4. So your A is actually minus 4. Now we will go for the ones complement. So we have what? 1, 1, 0, 0. 1, 1, 0, 0, what does it mean? It means it is a negative number, right? It's a negative number because of this sign bit, which is 1. It means it's a negative number. So we want to find the value of it. We just have to take the ones complement. So what we'll do, we'll take the ones complement of this. That will become 0, 0, 1, 1. And this magnitude is 3. Okay. So that means this number, that means what does this number 110 imply? It means its value is minus 3. means its value is minus 3. So your B is actually equal to minus 3. So your A is minus 4, B is minus 3. So let us write A is equal to minus 4, B is equal to minus 3. Right? Now, in the question, what they're saying, they want to find what one's complement of B minus A. So first, let us find what is B minus A. B minus A is what? Minus 3 minus of minus 4. Right? So it is minus 3 plus 4. So that is equal to 1. Right? 1. Okay. So now 1 you have to represent in terms of 1's complement. So 1, you know how it is? It is 0, 0, 0, 1. And its 1's complement will be given by 1, 1, 1, 0. Okay. All right. So that is the answer. 1, 1, 1, 0. Okay. We'll try the next question. Okay. Question number 8. So this is the number A, this is the number B. There are two 8-bit sign 2's complement representation numbers. Okay, we want to find the product of them and how do you represent it in 2's complement. Okay, so we know A that is equal to 1, 1, 1, 1, 1, 0, 1, 0. This is the number which we, so again you have 1, 1, 1, 1, 1, 1, 0, 1, 0. Okay, and B is 0, 0, 0, 0, 1, 0, 1, 0. This is very simple. This is 2 plus 8 that is equal to 10. So your B, you get it to be 10. Now, A, so what does A actually signify? This again, you know, this is minus 2 raised to 7, 2 raised to 6, 2 raised to 5, 2 raised to 4, 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0, right? And this we already checked that minus 2 raised to 7 plus 2 raised to 6 plus 2 raised to 5 plus 2 raised to 4 plus 2 raised to 3. This, it will come out to be minus 2 raised to 3. Okay, it will come out to be minus 2 raised to 3. You can have a better way of saying how it is. Let us say we start from 2 raised to 3. So this 2 raised to 3, this is 1. 2 raised to 4 is 2. 2 raised to 5 is 4. 2 raised to 6 is 8. And 2 raised to 7 and minus of that is minus 16, right? So minus 16 plus 8 is minus 8. Minus 8 plus 4 is minus 4. Minus 4 plus 2 is minus 2. And minus 2 plus 1 is minus 1. So this is equal to minus 2 raised to 3. Okay, this is another way you can do this thing fast. So minus 2 raised to 3. So that means your A is actually equal to minus 2 raised to 3 plus 2 raised to 1. So that is minus 2 raised to 3 is 2, 4, 8 minus 8 plus 2. This is equal to minus 6. Okay. So now what we have got is, we have got A is minus 6, B is 10. So A into B actually will be minus 16. So we have to represent minus 60 in 2's complement form. Minus 60 has to be represented in 2's complement form. So easiest way is you can write A into B, this is minus 60. It is actually minus 64 plus 4, right? So if you again take this There's 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7, uh, 2 raised to what is 64? 2, 4, 8, 16, 32, 64. So it is 2 raised to 6. So that would be your 2, no, 2, 4, 8, 16, 32, 64. Okay, so 6. So this is 1. This should be 1. And plus 4 means 1. And you need minus 64. This is minus 2 raised to 7. So you have to make this. So it will be 1, 1. Then you have 0, 0, 0, 0, 0. Okay, this total would mean minus 16 2's complement, right? Okay, so it is difficult to want to do it. So let us go for another way. Let us go for another way. So we know we have to first find what is 60 in the normal binary. 60 in normal binary, what is it? What does it mean? 60 in normal binary could be can be written as 32 plus 16 is 48 plus 8 is 56 plus 4, right? So this actually means 60 is 0, 0, 1, 2, 3, 4. 0, 0. This one's complement is equal to 1, 1, 0, 0, 0, 0, 1, 1. Now you will add 1 to it. This becomes 0, 1, 0, 1. You have 0, 0, 0, 1, 1. So this is your 2's complement. This is actually a minus 60. And if you will see it, it is same as the top one as well. Let me zoom out. So this and this are the same. Okay, so in two ways I went, like it's a roundabout manner. I've gone and shown you two different ways in which you can represent it. But this is for you to, understand there's not only one method. There's not always only one method. There are multiple methods. And as you'll be going for competitive exams and GATE exam or own subject exams, you should understand there are multiple methods. You try to find a method which works for you. If there's a better method which someone has followed, also you can use that, incorporate that. Okay, you can improvise always. Okay. So now we'll go to the ninth question. So this has the concept of adder. Okay, it has the concept of adder. So let us first try to understand some bits about adder. What does adder do? What does it mean, etc. So you have an adder. What does an adder do? It is just for addition. We are adding it. So there are two simple blocks which you know. One is a half adder and one is a full adder. Half adder, it has no carry input. Okay, it has no carry input. Full adder, it has a carry output. Sorry, it has a carry in. So let us look into it. So if you see, just now we did this. What we did was we added these two, right? These two. So if you see what I did 1 plus 1. I have done over here 1 plus 1. It got me 0. That is the sum of it is 0. And then I had to carry 1 over here. Then 1 plus 1 again I got output 0. Then I had to carry 1 over here. Then I got output 1, right? So this is how you are adding. So you get a sum, you get a carry. So over here, there was no carry input. There was just 1, 1. But over here, over here, you have a carry input also has come. That is, this is your carry input, right? So you can have blocks. Like you can have, this is a half adder. Half adder means what? You have A, you have B, you sum it up, you get the sum as well as you could get carry, because carry also can happen, right? Although you're adding only one bit at a time, you get a sum and you get a carry, right? So this is your half adder block. But there can be a case where you need a carry input. That is, a carry of one stage has to go to the next stage, right? Over here, the carry of this stage had to go over there to the next stage, right? That is why you have what is known as a full adder. The full adder, how it is? It is quite similar. You have A, you have B over here, but you also have a carry input. And then you generate S means the sum, and this is the carry out. Okay. So this is the slight difference between a full adder and a half adder. A full adder can be constructed by using two half adders and an OR gate and everything. That is possible, but just I want you to understand the significance of it. Okay. So then let us consider this. What does the question 9 say? Still the screenshot first. Or let me explain the ripple carry adder, then I will touch this question. So we have what is known as a ripple carry adder. Okay. Let us say we confine ourselves to 4 bits. So this is one full adder, right? This has some A0, B0, and this generates a sum output and a carry out. Okay. Then you have another full adder. This has your A1, this has your B1, and this carry is the carry out. This is the carry in for this. And this is your sum 1, and this is your carry 1. Then you have your next full adder, right? It has your A2, this has your B2, and this carry 1 is the input for this full adder. This generates your sum 2, carry 2, and this is again your full adder, right? And this carry 2 has to go here. This is your A3 and your B3, and this generates your sum 3 and your carry 3. So what are you doing over here? You're actually adding A plus B, okay? Where A is actually what? A3, A2, A1, A0, right? B is B3, B2, B1, B0. We are adding them. What will our output be? Our output will be S0, S1, S2, S3, and we get a generated output that is carry 3. Okay, this is your effective carry 3. And this will go to the next stage. This will go to the next stage. Okay, so this is what it signifies. We have done many, ones complement, two's complement. In two's complement, we add that one. We can do addition, etc. So that when you go to the hardware, when you go to the actual hardware block which will do addition, it is something similar like this. Okay, so this is well and good. But now there is a delay. Like in everything, in things in life, there is always a delay. Why is there a delay? Because as we saw in the first week, and second week as well, if I'm not wrong, the switch has to turn on, turn off. The NMOS has to turn on, turn off. PMOS has to turn on, turn off. All these things are there. So there's a delay. It is not instantaneous. It has a finite time. So those contribute to delay. So when you have a logic gate, you also will have a delay. So what is the implication of that delay? So let us first see the question and then we try to solve it. So you have a 1-bit full adder. Okay. So this is like your, what is this? This is your 1-bit full adder, right? Because it is taking 1 bit A0, it is taking another bit B0, and then it is doing addition. So that's why it is a 1-bit full adder. Okay. So now, just could you give me 1 minute? I'll just come in 1 minute. Huh? Sorry, there's like a kind of very heavy breeze, so I think one storm is coming. So I have to just remove my clothes, okay, from which were hanging. So okay, so we were thinking what we were doing. We were doing the question one bit full adder. So there is a delay. There's a concept of a delay. So you have a full adder, right? Where you get the input bits. Let us say you have input bits. Just draw the same convention. You get the inputs A0 and B0, right? And then you get your outputs sum 0, carry 0. Hmm. So to produce the sum, and it also has a carry in, okay? It also has a carry in. Produce the sum takes 75 nanoseconds. Okay, 75 nanoseconds. And to produce a carry, it takes 60 nanoseconds. Okay, produce a carry, it is taking 60 nanoseconds. Now, what does it mean? Like, what does it imply? Let me look into it. So, as we have seen over here, let's just go again. Let me draw. You have your full adder here. This is your carry in, which is not used in the first stage. So you have A0 here, B0 here, S0 here, C0 here. Okay. Again, you have full adder here, A1 here, B1 here, and this has to go over here, right? And this is your C1, S1. So let us start over here. So at time t equal to 0, okay, you will apply A3, A2, A1, A0, B3, B2, B1, B0. Very good. You have applied all of them concurrently, simultaneously at the same time. Now what happens is to produce your sum, it is taking 75 nanoseconds. To produce this carry, it is taking 60 nanoseconds. Okay. The problem is this 60 nanosecond, this has to go over here, but it is not there for the first 60 nanosecond. So it has to wait. So 60 nanosecond has to elapse. Once that 60 nanosecond has happened, now S1 will produce. Now S1 and C1 will come. So this S1 and C1 will come at a time of 60 plus 60, that is 120 nanosecond. And C1 will come at a time of 60 plus 75, that is, what is 60 plus 75? That is 135 nanoseconds. Okay. Then you have another full adder, right? You have another full adder. This has your A2, B2, you have your C2, you have your S2, and this is going over here. So at this time, it has become 135 nanosecond. So S2 will then, it will become 135 plus 60, that comes out to be 195 nanosecond. And C2, it is 135 plus 75, right? Oh, sorry. I made a mistake. Carry 60, sum is 75. So sum would be 7. So this would actually be, sorry, this is interchanged. Mhm. So sum is, so 60 plus, so here it is 60 nanosecond. 60 nanosecond, sum you add 75. So 60 plus 75 is 135 nanosecond. And what to generate carry, it is taking 120 nanosecond. Okay. So this comes at time of 120 nanosecond because I want carry. It doesn't matter if sum is not generated. I need carry. Carry has been generated in 120 nanosecond. I will use that. So then S2 will be generated in 120 plus 75, that is 195 nanosecond. And C2 is 120 plus 60, that is 180 nanosecond. Okay. Now I have another full adder, right? It has my A3, it has B3. Now this goes over here. This will produce my C3, this will produce my S3. Now you must remember the time has become 180 nanosecond. So 180 plus S3 takes 75, so it becomes 180 plus 75, 255 nanosecond. And for to produce C3, it becomes 240 nanosecond. Okay. So the result of my addition, that is my A plus B, that is my A3, A2, A1, A0, and B3, B2, B1, B0. The result of this addition would be what? S0, S1, S2, S3, and carry 3. So I need to see how much time it is taking for me to generate all of them together. So that is the maximum, how much time? You see the maximum is 255 nanoseconds, right? This 255 nanoseconds. So the time that it takes to convert completely to the addition properly, correctly is 255 nanoseconds. Okay, so this is the time which it will take to compute it. So if you see over here, it is 255 nanoseconds. So how many 4-bit additions? So what will be the minimum propagation delay? Okay, the delay, what will be the minimum propagation delay for getting the results? That is 255 nanoseconds. That overall thing you see from your input to your output, how much delay it is taking. Delay could also be more. But what is the delay which is taking? That we calculated it to be 255 nanoseconds. And how many 4-bit additions per second can be expected from this design? If you want to go at the limit, that is, it does one addition. Immediately after it does one addition, you start the next addition, next addition, next addition. At that rate, if you go, then the number of conversions, the number of additions which you can do would be equal to 1 upon 255 nanoseconds, right? 1 upon 255 into 10 to the power minus 9. That your number of additions is actually 10 to the power 6, actually 1000 into 10 to the power 6 by 255. Okay, that will get you some 3 point something, which is same, 3.92 to 10 to the power 6. Okay, so this is the question regarding propagation delay. We'll go to the next question. If this is the value, you need to find out x. Okay, you have to solve the value of x. So there is 3. It's in 3 number system of 3, right? So if it is a number system of 3, this value, that is your 1110212.20211. This is the value. Now you have to convert it. Okay. You will, how do you have to convert from this 3 to 9. You have to get it to 9. Now, I want you to think, if you convert it all to binary, that is, if you have 2 here and you have 1 here. Let us say 1, 2 in terms of 3. What is the magnitude? That is 1 into 3 to the power 1 plus 2 into 3 to the power 0. So the maximum that it could take is 2 to the power 3 to the power 1 plus 3. So it becomes 9. Okay. All right. This is what we need. That means if you have, let us say this in 3. Okay. Its maximum which it could take would be what? 2, 2. That is 2 into 3 to the power 2 plus 2, which is actually 2 into 9 plus 2. That is 18 plus 2. That is 20. Okay. So this can be the way. We'll have to actually convert it completely into in terms of 10 and then convert it to 9. Okay, so we need to convert it from number system 3 to number system 9. So let us basically go to the number system which we are most comfortable. That is, we convert it to number system 10. So how do we get it as? How do we write it as? So this is the main part. That is, we'll say 1 1. The question 1 1 triple 1 0 2. So you have triple 1 0 2 1 2 1 2.2 0 2 1 1 2 0 2 1 1. So what do we do? This is, we'll start with the integer part. We'll start from 2 into 3 to power 0 plus 1 into 3 to power 1 plus 2 into 3 to power 2 plus 0 plus 1 into 3 to power 4 plus 1 into 3 to power 5 plus 1 into 3 to power 6. So the integer part, when you will add it, that is 2 plus 3 plus 9 into 2 is 18. 3 into 4, 9, 81 plus 3 to power 5 is 3, 243 plus 243 into 3 is just 243 into 3, 9, 12, 2, 1, 729. Okay, okay, that is 9 cube. When you sum it up, you would get, oh, let us sum it up. 2, 9 plus 3, 12, 13, 21, 24, 26. So 6, 2, 4, 6, 2 plus 2, 4, 8, 12, 13, 1, 8, 9. It is 936. Somehow I think I made a mistake. What is the blunder? Value is not coming as I had calculated previously. Mm, We used the 3 to power 0 is 2, 3 to 1 is 3. We then 2 into 3 to power square is 9 into 2 is 18. And 3 to power 4, 3 to power 5. 3 to power 3, 9, 27. 27 into 3 is 81. 81 into 3 is 243. So 3, 3, 9, 27, 81. This is 81. This is 243. This is 729. Where am I messing up? Let's check my calculator. 3 raised to 4 is 81. 3 raised to 5 is 243. 3 raised to 6 is 729 plus 243 plus 18. 1 plus 18 plus 5. Suppose it will 1276. Where have we made the mistake? Control Z. This 2 plus 3, right? And here 729. So actually the 729 plus 243 plus 181 plus 18 plus 5 is 23. So when you sum it, you will get 3, 4, 7 plus 9 is 16. So 6 and 1. 3, 4 plus 6, 7. 9 and plus 8 is 7. 7, 1. 7, 8, 9, 10. So it is 1076. Okay, so it is correct. 1076. Now, the fractional part. The fractional part, Not responding. Let me wait for some time. Okay, we got it to 107610. Okay, sorry for the confusion. It was 107610. So now, how do we convert it to in terms of 9? So we have three options. It could be any of these options. So 1076, so it should be more than that, right? So let us start with the fractional part. Okay, what about the fractional part we have not done? So the fractional part, mhm, fractional part is given by 2 into 3 to the power minus 1 plus 2 into 3 to the power minus 3 plus 1 into 3 to the power minus 4 plus 1 into 3 to the power minus 5, right? So this, when you will do the multiplication and addition, you would get 2 into 3 to the power minus 1 plus 2 by 27 plus 3 to the power minus 4 plus 4, 3 raised to minus 5. So you get it to be fractional part is 0.7572. Okay. So in the answer, let us start with the fractional part. Let us start with the fraction. 0.673 is the one which is common, and 0.757 is another thing which is common. So it cannot be 0.757 because that was we got for terms of x10. So it has to could be 0.673. Let us check. Okay, let us see 0.673 in terms of 9. What is this corresponds to? 6 into 9 to the power minus 1 plus 7 into 9 to the power minus 2 plus 3 into 9 to the power minus 3. So that is what 2 by 3 plus 7 by 81 plus 3 by 9 raised to 3. Okay. You added 2 by 3 plus 7 upon 81 plus 3 upon 9 raised to 3. This also becomes equal to 0.7572. Okay, so this fractional part is correct. Now we have two options which we need to check, 1425 or 1225. Let us start with 1425. 1425, this is what? 1 into 9 to the power 3 plus 4 into 9 to the power 2 plus 2 into 9 plus pi into 9 to the power 0, right? So this is 729, 4 into 81 plus 18 plus 5. So the 729 plus 4, 324 plus 23. So that becomes equal to 7 plus 9 is 16, 6, 1, 4, 5, 7. 3 plus, so they 1076. So it's got the correct answer. So the answer is 1425.673. This is corresponds to 1076.7572 in terms of 10, or 1425.673 in terms of 9 is equal to 1 triple 10212. So triple 10212.20211. 20211. Okay. So this is the answer. All right. Okay, so instead of all this, there is a easier way which you can look into it. Let us see that. This 1110212.20211. Let us make it even number of bits. So let us add a 0 here. Let us add a 0 here. So we'll consider this and this for the time being. So we have 1, 2. 1, 2, what does it mean? It means 1 into 3 to the power 1 plus 2 into 3 to the power 0. That becomes equal to 3 plus 2. That becomes equal to 5. Which is this 5, right? Similarly, 2, 0 actually is 2 into 3 to the power 1 plus 0 into 3 to the power 0. So that is 6, which is this 6. Okay, there was an easier method. You don't need to do all this math, everything. There's an easier method as well. Similarly, 21 is corresponds to 7. 2 into 3 to the power 1 is 6 plus 1 is 7. And this 2 to the power, 1 into 3 to the power 6, this is 3, right? The 0 2 corresponds to 2. 1 1 corresponds to 3 plus 1 is 4. 0 1 corresponds to 1. Okay, so, and this is 5. This is 6. Okay, so there's an easier way. I apologize. We could use this easier way also to get the output. Okay. Next, we can check this sum. In which of the following signed additions using 4-bit adder does the overflow condition takes place? Assume that MSB represents a signed bit. Negative number MSB equal to 1 are represented in 2's complement form. Okay, so let us say question 11. We have concept of overflow. Overflow occurs when you do signed numbers addition and both numbers have the same sign. Okay, both numbers have the same sign. If the numbers have different signs, then overflow doesn't happen. So in the question, what you can see that 5 and 6, they have different signs. So wherever 5 and 6, that is the wrong option. Okay, so either it is 1, 2, 4, 2, 3, 4, or 1, 2, and 3. So when you will do the addition, you would see that the sign, the bit sign of the MSB bit or the sign bit will change for 1, 2, and 3. For the fourth case, it remains the same. Okay, so the answer would be A. Sorry, it would be C in this case, 1, 2, and 3. Okay, so I'll also just show one simple simulation. This is a half adder circuit. Okay, let us see this. So this is a clock which is used to drive an up counter, so that it will generate a possible combination of the two bits. That is okay. Let us see. We have A and B. So it is 0, 0 here. Then you have 0, 1 here, 0, 1. Then you have 1 and 0 and 1 and 1. So these generate the possible combinations of your two input states, right? Two inputs can have four possible combinations. This is how it is generated using an up counter. Okay, so this is your input A and your input B. Now your carry is A and B. So that is come over here. Carry is A and B. And your sum is A XOR B. That gets represented over here. Okay. So this is how an half adder you implement. So this is actually a half adder. You have A is your input and B is your input. You're trying to add it. So when A is 0, B is 0, your output sum is 0, your carry also is 0. When A is 1 and B is 0, your sum is 1, but there's no carry. When A is 0, B is 1, your sum is 1, but there is no carry. When A is 1 and B is 1, your sum is 0, but your carry is 1. So this is how you represent the logic. Okay, this is how you can represent your half adder. Okay, I tried to do full adder, but there's a limit in the size using elements. I'll have to look for a different software to simulate these digital circuits. Okay, these are very intuitive, give you good understanding of how you get the sum A, B, etc. Right? Okay, so thank you for joining. I'll end the session. Hope to see you next week.